Welcome back. Welcome back. This is a lecture for section 4.1. However, one of you guys is going to probably laugh a little bit, but an advisor told me that someone wanted to know where I got my backdrop from because of all the squishmallows. They're all Bigfoot or Yetis, and they came from my daughter and her friend and some friends. What you can't see is I also have some sitting on the edges, bigger ones. My daughter is bound and determined to get me all of the Bigfoots and Yetis squishmallows. And just so you know, she's 26. So she's a little bit addicted. So if there's any of you out there, it's a toss up which one of us has more squishmallows right now. I have more upstairs. So yes, this is my living room. With that, let me proceed on to 4.1. Because I was laughing about where to get my backdrop. No, that's the back wall of my living room. So 4.1 is about linear regression. And this is actually kind of a key point with statistics. It's one of the hot topics. A lot of your statistics is done through regression lines. And with that, I give students heads up. You want to make sure you understand chapter 4 because you guys are coming close and getting real close to something called a midterm. And guess what a good chunk of the midterm is about? Regression lines. So you need to make sure you get sections 4.1 and 4.2 under your belt well. So with that being said, let me share my screen and we'll get to it. I have a data set, and that data set is what we're going to come play with. It is also out there underneath modules, so you can download it. But this is set. I'm going to put this diagram notes up because this is what I'm lecturing from. So there's two sets of diagram notes. One goes with Tyler's, one goes with mine. These are the ones I lecture from. They're a little bit more cut and dry. But you can copy paste straight from this. At least that's how I have it set. But it starts out saying it is important to start with a picture. Now, I stressed the reason why we did box plots previously, because the reason why we do box plots is to tell whether or not we have data that is skewed or not skewed. I can make a histogram line, quite good at it, by playing with class widths. However, I can't make a box plot line. So something so simplistic statisticians use because it tells us whether or not our data is skewed. All right. We want it to be bell-shaped. We have more tests and things we can do with the bell shape than we do when it's skewed. So we start with a picture. Well, when we're doing linear regression, we start with a picture, and the picture we start with is a scatter plot. Now, there's a reason for it. Here are 5 different versions of a scatter plot. The biggest reason why we run a scatter plot is one, we want to see, does it have a shape? Because this is called linear regression. That means we want data that looks like this or this. This is considered a positive. This is considered negative. Think back to your graphing of linear lines. Well, we're going to create a linear line through the data. Sometimes you'll hear this referred to as the best fit line. That's the same thing. But the reason why we run it is one, what if it's not linear? What if we get a shape like this? You tell a computer to run a straight line, to tell me the regression line through that, it'll run a straight line through it all right. It'll try to do it kind of like horizontal, but it's not linear. that it takes us to visually see, because the computer's out thinking, as I put it. You tell it to do something, it's going to do it the best it can. It doesn't understand the critical thinking, at least not yet. So we run the scatter plot to look for shapes like this and this. This is what we really want to see. We want to see a tight linear pattern. We don't want to see this. And we definitely don't want to see this. These are both nonlinear. Now, the reason I stress this is that you're going to also learn that we next run a test. The test is for the R, or the correlation coefficient. Well, here's the problem. If I run that same test on these, I'm going to get a high value, which is what I want. But guess what? I'm also going to get one here because the pattern's tight. So we start with the picture of a scatter plot to look for shape. Now, this is where me and Pearson is going to disagree. This one, we never say no relation. Remember, I said way back in the beginning of the semester, we never make absolute statements. Well, don't you think saying no relation is an absolute statement? You're right, it is. What we typically say is no to a very weak relation. We do not say no relation, because a lot of times this will still throw a code. This will still throw an R factor or an R correlation code. It's just is going to be very small. So this just basically goes through. We say something is positively associated when it looks like this. We say it's negatively associated when it's like this. Well, I'm also going to give you a hint. This will also throw a positive R, and this one throws a negative R. So if it's positively associated, you're going to get a positive R. Negatively associated gives you a negative R. All right? And that's what they're talking here. This is positive, this is negative. As the X, and how we describe this is as the X value increases, the Y value decreases. Now, Pearson's homework tweaks on that is because it's going for understanding. Because sometimes it'll say as the Y value increases, the X value does what? Well, as the Y value increases, the X value increases. As the Y value increases, the X value decreases. They say it in reverse, and that's some of the homework. I'll give you a heads up. However, when we go to interpret or tell the story, we talk about as the X increases, what does the Y do? Because the X value is the explanatory variable. The Y value is the response variable. Yeah, we're starting into X and Y, two variable stuff. Now, R, it runs from -1 to 1. It will never be bigger than 1. Never. The closer to 1 it gets, the higher the correlation, whether it is a positive 1 or a negative 1. This bit is saying if it's a positive, it is a positive linear relation. If it's negative R, it's a negative. I have never seen 1. I have never. We get real close to 1. I've never seen a 1. So this is just going through and describing what the values mean. I'm about to kind of give another chart. So if R is close to 0, it does not imply no relation. It's just this is one kind of restatement. It's no to very weak, because there I've seen, because it's like, yeah, it's really scattered. I mean, we're basically saying it's no to very weak. All right. Again, it replies it. It's also R is unitless, and it's not resistant. In other words, if we get some little outliers out there, it does affect the value. So how do we know? Well, sadly, this is where I wish I could say that statisticians agree. Okay. This is getting into gray matter. I can show you different charts on the strength relationships of the R. All right. And see if I can just type here. Yeah, I'm going to drop this down a page. Because it depending on who, basically I've come to decide it was who taught you the scaling is what you believe. I have seen, again, several different scales. I was taught, along with one of my counterparts, we were taught the 25 scale. And what does that mean? When R is between 0 to 0.25. We say it's very weak. 0.26 to 0.5, we call it weak. 0.51, 0.75, we call it moderate. 0.76, point to 1, we call it strong. Now, does it mean it's cut and dry? No, it doesn't. Remember, it's kind of grayish, and this is the part really kind of distraughts people. And these are absolute values. Okay? I am talking the absolute value of R. Remember what an absolute value is? If it's negative or positive. The negative or positive in the R tells you whether it's negatively correlated or positively correlated. It's the pure value of R that I'm talking about right now. So if I had an R value of negative 0.28, I could say it is negative let's do it this way. I could say it's a very weak to weak negative correlation. It's not exact. Just because it's so close to the cutoff, I could overlap these two. It's okay. Or I could just say it's weak. What I would not say that is a strong, it's too low. Nor would I say it's moderate. It's too low into this category. But it's so close to these two that I could overlap these two. The negative part comes in from the sign. So let me give another example. If I had a 0.77 or correlation, I could call that, you see how it overlaps these two? I could say is a moderate to strong positive correlation. What I would not call it is weak. Or I can just call it strong. But it's more like this chart is more of a guideline. And the sign part comes into whether it is this portion of the sign on the R is how we put whether it's negative or positive, period. And then we just look at the absolute value of it. All right. The key is the absolute value. So let's look at some of these. This says, see how that is? I mean, it's just a perfect line. That's a positive R of a 1. D, that's a negative 1. But let's look at this. See how tight this scatter plot is? And it's going up as the x increases, the y increases. That's a positive, and they're calling it a 0.9. This one, they're calling 0.4 moderate. Remember, different schools of thought. Again, it's as the x increases, the y is increasing. So it's a positive correlation. This one, as the x increases, the y is decreasing because it's a negative. And they're calling this one a 0.9, but a negative 0.9. See how strong? See how strong? This one's got some scatter to it. They're giving it a negative. This one, they're calling a no correlation. Yes, it is going to be close to 0. Again, I would not call it no. I would call it no to weak. Because if I add a little bit more data, I mean, I could shoot a line like that. I could. It's not going to be a pretty line. It's going to have a very poor correlation. I see why they're saying no, because it also, if you kind of look at it, doesn't it kind of hump a little bit? Now this one, it's definitely got a defined hump. So when we run the pictures and look at this, when we get things like this, we're not even going to bother to go any further. We're not going to run the tests. I'm not going to. I'm going to say that's nonlinear, that last one. It's just nonlinear. It's got a 2 defined of a hump. This one, I would run the test. On G, I would run the test because, yeah, it kind of does have a hump, but I can also put a line through it. So I want to see what type of correlation it has. That's where the final decision is going to come, is the R factor on something like this. All right. So match the appropriate scatter plot. We have 4 values. I like to start with the highest one because I look for the tightest pattern. And looking at that, crank this down a little bit so we can get it all on screen. If I look at this, which one has the tightest pattern? Well, it'd be this one. So I'd call I, or 1, negative point. So that one is gone. All right. The next tightest one, I kind of work backwards. I'd say it's 4 because the tighter the patterns are the easier ones to find. So I'm going to say 4, or let's go ahead and keep it. I'm going to say, because it's positive too. So that's my 0.8. So I've got 2 of them out of the way. That leaves me a 0.1 and a 0.5. Well, the smaller the R, the less, or the smaller the R, the more scattered the dots, the less of a pattern. So looking at this, which one do you think has the least pattern? Is it 2 or is it 3? I mean, we could kind of see a pattern here, and we definitely see a pattern here. This one, this is my 0.1. Look at this. Yeah, we've got, if I take out this one dot, do you see how it makes a line? It's this one dot. Remember it said R's are affected by outliers. Well, that right there is an outlier. I can tell you from looking at so many of these. So because of that, if I take that one dot out and look at it, yeah, I've got a correlation. So this is the one I'm saying is going to be a 0.5. And the third one then will be my 0.1. All right. On the underneath modules, you will find there's an app out there. You can play a little bit playing the games of trying to guess. There's a game out there. As odd as it sounds, yes, as mathematicians are geeky, we like to play computer games, seeing if we can figure out the correlation coefficients. Not me. Sorry. So, how do we calculate a linear correlation coefficient? This is the reason why I'm using the elephant age. I want to see, is there a correlation between an elephant's age and the trunk? In other words, I want to see if the older the elephant, does it predict the length of the trunk? There is got to watch how you put these in. Well, I'm going to go over to StatCrunch. And I'm making sure that when I make the jump, it goes with me. So I've already got the data downloaded. By now, I'm pretty sure you guys are getting good at putting data into StatCrunch. All right. Well, I clicked on the wrong thing. Let's go back to this. What I've done is I clicked on the thing and closed the tab. All right. I apologize for that. All right. I've got it back. Now, I was nice because widen this out a little bit. I'm telling you which one's the X and which one's the Y. The X values are your explanatory variables, your Y values are your response variables. That we take the X to predict the Y. This is going to be important in 4.2. So how do I do it? All right. I can do it in more than one way. But I'm doing regression, simple linear. So I went to stat, regression, linear. It's telling me to select which one is my X, which one's my Y. In the future, just so you know, I'm not going to label X and Ys. So my X label is what? Elephant age. My Y is trunk length. Compute. Now, look at this. You notice all I did was I hit to the right. And it is showing me my scatter plot with a line through it. I typically do not like students going straight to this because guess what? Once you see a line, you can't unsee it. But the part that you're looking for right now, do not use the R squared. We don't use the R squared. It's the R correlation coefficient. That's what you're looking for. And you take it to 3 digits. So our R is 0.847. All right. And we have a sample size of 21. That's going to be important here in a minute. Okay. Now 0.847 doesn't seem bad, does it? And if I was just looking at the picture, I'd say we got a decent linear line, don't you? It's not perfect. But looky here. We have an outlier. I can tell you that right now. We have another outlier. So if I was to do a box plot on this, I'd find outliers. Okay? That's one way. Now, if you just want to look at the graph, you go to Graph, Scatter Plot. We select the X, we select the Y. Yep, I was thinking there's something else I wanted. And then I could put the titles on it. I want you to look at this. This is the pure scatter plot. And if you used to look at that right off the bat, what do you think? Does it look linear? Yes, it does. So that means we proceed with the test. Now, what is the test? That's the reason why we need these two numbers. All right. So let's go back to this. Is there a correlation between an elephant's age and trunk length? All right. From the scatter plot, there appears to be a positive linear correlation or relationship or association. I never can spell that. So how do we truly determine it? I'm going to scroll down. Right here, we compare the R value versus the correlation coefficient. And how is this read? 1, the R has to be bigger than the critical value. So remember I said sample size was 21. Well, that's what this column is. So I come down where N equals 21 right there. Let me highlight that. Nope, won't let me. Won't let me. Yeah, I can do it this way. Right there. N equals 21. So right there, my crit value is 0.433. So we calculated this, and you heard my first statement. It appears to be. That's the first start. This is where I'm asking, is there a linear? In other words, I'm asking about the shape. It's down here when I bring in the actual test, because if I didn't see a linear shape here, I would not progress to example 4. So again, what was N equals, oh, I hate autocorrect. My R was what? 0.847. My crit value was 0.413. Since R is greater than my CV, there is a positive linear correlation. However, remember that chart? What's the strength of the correlation? Well, at 0.843, I would say it is a strong positive. Positive linear correlation. This is the final statement. Most of the time, we will make some statement to make this complete statement. We really should have numbers in here also. But as long as you guys tell me this and then make this, I can make a little bit of a leap. All right. Tell me grammar. Why? Oh, it's because I didn't put a period. Oh, gee. All right. So when we make these final statements, you need to make sure you include the strength, positive / negative, and the shape, which in this case should always say linear. Unless you have something that when you run the shape and it has a hump in it, and I'll be honest, most of the time, if it doesn't have a real distinct hump, I won't declare it nonlinear yet. I will tell them need more data. Because a lot of times what happens when you get let me scroll up, something like this, if we get more data, maybe this guy's an outlier. If I get more data, this part fills in. Also, see how this has a mild hump? This would be one that I'm like, I'll run it, but then if it comes up to where it's really nothing, I'd say we really need more data. So that's not that many dots. So a lot of times in this, when we add more dots, you'll see this fill in more. This is still kind of a lousy correlation. I'll be honest, it is. It'd be a weak one. All right. So ladies and gents, well, that's weird. When I highlighted, it moved. It moved. So anyway, the biggest thing that I want to remind everybody, and I can't scream this enough, I'm going to put in red. When you make your final statements, you cannot say causation. Observational data, observational studies can only have associations or correlations. We cannot say causation. They give a one, there was just about percentage of married and unmarried and this and that. Bachelor's degree with higher percentage of births to unmarried mothers. Now, let me put it a different way to kind of bring this home. I love when they can do this. Did you know that there is a correlation between shark attacks and ice cream sales in Florida? Yep, there is. So if I can make the statement, and there's a study, because of that, I can't say eating ice cream causes the shark attack. It's kind of funny, isn't it? There's also another study where you can say ice cream sales in New York City increases murder rates, causes murder. Huh. Both of those are a little bit absurd, but it's using the absurd to make a point. It's because of lurking variables. Pretty sure the lurking variable with shark attacks and ice cream sales is the fact it's summer months. Summer months, ice cream sales go up. Well, so do shark attacks. I'm betting it has something to do with the fact it's heat and more people are in the ocean than in, like, say, January. So it does come down here and talk about, for example, ice cream sales and crime rates have a and it does. It's really high. I laughed when I found that out. So does eating ice cream want to make you go out and commit crimes? Maybe we should ban ice cream because I mean it's causing shark attacks and crime. Yeah, no. Again, crime rates go up in the summer months. More people are out and about. Same with the murder rates. It's the fact that we're out and more accessible, you might say, to the criminals. And with the higher temperatures, we eat more ice cream. So there are two absurd reasons illustrating why you cannot say on an observational study with causation. Now, with that being said, you got to watch people interpreting studies. Because a lot of times you get in the media, this is me telling you about, listen carefully to what, like, the news and everybody says. The study itself will say causation, and then the next thing you know, they're reporting it's the secondhand info. Think like when we were all young. I don't know about you, I played a game called Grapevine or telephone, where one person said something and you whispered it to the second person whispered it to the third person whispered it to the fourth person, and the next thing you know, by the time it got all the way around the room, it changed. Well, that's kind of the same thing that happens here. A study may have been done, someone reads it, and then they interpret it again. And the next thing you know, we have an observational study that's being said we have causes. One of those type of studies, I'm going to bring it up, and again, I'm bringing it up, and it's a political hot button, is climate change. I am not a climate change scientist. Nope. But you hear that we are causing climate change. Well, are we purposely tweaking certain variables while holding other variables steady? The answer to that is no. What we're doing is that we are observing what is going on and seeing a response happening. Yes, climate change is based off an observational study. Shock, shock. That's my problem. When I hear that, I kind of cringe because I know what type of study they've ran. It's a historical look back. Again, what is an observational? It's a look back. We look back historically. and we didn't hold variables steady. There was no experiment done. Only with experimental design can you state causation. So climate change is not an experimental, it's an observational. We cannot say it's a causation. What we can say is there is a correlation between the two. Slight change, but one causes more of a emotional response, while the other one causes a little bit less. If I hear there's a correlation, okay, what's the correlation? Do we have any ideas what factors could be? But you tell me this is causing this is more defined, more definitive, and we can get a higher response out of people. All right. So again, I am not saying one way or the other. What I'm telling you is I'm not a climate change scientist. What I am is a statistician, and I'm telling you what their flaw is. That is it. All right. So nothing more. But yeah, it's an observational study. Can't have causation statements. So next time you hear that in the news, say, busted. All right. This is it for this evening. I hope you guys get through this. I'd recommend going through this slowly a little bit, because 4.2, we're going to actually start doing some linear regression, right? Good luck, guys.